Hello everyone, welcome to Digital Communication Tutorials. In this video, I am going to take up the 12th numerical on waveform coding techniques. Please note this is a numerical on delta modulation. Let me read out the question first. Consider a low pass signal with a bandwidth of 3.4 kHz. A linear modulation system with step size small delta equal to 0.1 volt is used to process this signal at a sampling rate 5 times the Nyquist rate. Part A of the question says, evaluate the maximum amplitude of a test sinusoidal signal of frequency 1 kHz which can be processed by the system without slope overload distortion. Part B of the question says, for the specifications given in Part A, find the output signal to quantization noise ratio under the first part pre-filtered and second part post-filtered conditions. Right, by reading the numerical, you would have understood that it is a numerical on delta modulation. Let us start with the solution part. Look at the very first sentence of the numerical. It says there is a low pass signal with a bandwidth of 3.4 kHz. So let us start with that part first. We know that the bandwidth of the signal also represents the maximum frequency content of the same. Therefore, the maximum frequency content of this low pass signal is also equal to 3.4 kHz. Further, we are told that this signal is processed at a rate equal to 5 times the Nyquist rate. So let us start by finding the Nyquist rate and then find the sampling rate. We know that the Nyquist rate as per the low pass sampling theorem is equal to 2 times the highest frequency component of the signal. Therefore, Nyquist rate would be 2 multiplied by 3.4 kHz. This is equal to 6.8 kHz. Further, the sampling rate is equal to 5 times the Nyquist rate. So, this would be 5 multiplied by 6.8 kHz. Okay, that's about the low pass signal that is given. Let us start with part A of the numerical. Part A of the numerical says, evaluate the maximum amplitude of a test sinusoid that has a frequency of 1 kHz. So let us start by defining the test sinusoid as g of t equal to a naught cos 2 pi f naught t. Where f naught is given as 1 kHz. Please note, this is not the same low pass signal that is given at the beginning of the numerical. This is a test sinusoid. Come back to part A and you will note that we are asked to find the maximum amplitude of this test sinusoid under the condition of no slope overload distortion. So let me start by writing the condition for no slope overload distortion. The condition is delta divided by Ts is greater than or equal to magnitude of d by dt of g of t maximum. Let me call this as equation 1. So now we are supposed to find the maximum magnitude of d by dt of g of t. Let me start with that. I am going to rewrite g of t here. Let me now differentiate g of t with respect to t. D by dt of g of t is equal to a naught multiplied by differentiation of cos is minus sine. So it would be minus of sine 2 pi f naught t multiplied by the coefficients of t, which is 2 pi f naught. This simplifies to, therefore, the magnitude maximum of d by dt of g of t is given by, this is equal to a naught 2 pi f naught. Let me call this as equation 2. Now I'll substitute equation 2 back into equation 1. So it is delta divided by Ts greater than or equal to A naught 2 pi F naught. Rewriting the equation for A naught, we get A naught is less than or equal to delta divided by Ts into 2 pi F naught. We know that Ts is equal to 1 divided by Fs. So the equation reduces to delta Fs divided by 2 pi F naught. Since we are asked to find the maximum value of the amplitude A naught, the less than or equal to symbol has to be replaced by equal to symbol. Therefore, A naught is equal to delta Fs divided by 2 pi F naught. Let us now start substituting the values. Delta is equal to 0.1 multiplied by the value of Fs, which we previously found as 5 multiplied by 6.8 kilohertz. So it would be 5 multiplied by 6.8 into 10 power 3 divided by 2 multiplied by pi multiplied by F naught. F naught here represents the test sinusoid, which is 1 kilohertz. The answer for this is 0.541 volts. This is the maximum value of the test sinusoid amplitude under the condition of no slope overload distortion. Right, that completes part A of the question. Let us now move on to part B. Part B of the question says, for the specifications given in part A, find the output signal to noise ratio under the pre-filtered and post-filtered conditions. Please note, when I say pre-filtered and post-filtered, we are referring to the low-pass filter connected at the delta modulation receiver. Let me start with the pre-filtered condition first. I'll start with the equation for the signal to quantization noise ratio at the output, and it is given by SNR output for pre-filtered condition is given by, we have the signal power divided by variance of the quantization noise, which is represented as sigma x square. Coming to the signal power, which is represented by P, it is given by the value of A naught divided by root 2 whole square. So P is equals to A naught divided by root 2 whole square, and the quantization noise power is given by, which is here representing sigma x square. For delta modulation, this is equal to delta square divided by 3. So I'll substitute these into the SNR output equation for the pre-filtered condition. This is equal to P divided by sigma x square equal to A naught divided by root 2 whole square divided by delta square divided by 3. This reduces to A naught square divided by delta square multiplied by 3 divided by 2. Let me substitute the values for A naught. We have previously found A naught as 0.541. So it would be 0.541 square divided by 0.1 square multiplied by 3 by 2. This reduces to 43.902. No units here because it's in terms of power. So expressing the same in terms of dB, we get SNR output in dB for the pre-filtered condition is equal to 10 log 10 of 43.902. This is equal to 16.42 dB. This is the answer for the output signal to noise ratio in terms of dB under the pre-filtered condition. Let us now move on to the post-filtered condition. The signal to noise ratio at the output for the post-filtered condition is given by 3 Fs cube divided by 8 pi square F naught square Fm. This is a derivation I have done in one of my previous videos. I'll leave a link of the same in the description below, or you can watch the same by clicking on the link shown in the top right corner right now. Let us substitute the values here. This is equal to 3 multiplied by, the value of Fs is 5 multiplied by 6.8 multiplied by 10 power 3. So, I'll write that here, 5 multiplied by 6.8 multiplied by 10 power 3 whole cube divided by 8 pi square multiplied by F naught is 1 kilohertz. So, it would be 1 into 10 power 3 whole square multiplied by the value of Fm is not given here. So, I'll just retain as it is. I will now assume that Fm is equal to 3 kilohertz. This is a generic assumption. So, Fm is equal to 3 kilohertz. Therefore, I will now substitute the value of Fm as 3 kilohertz. So, this reduces to 498.3. Once again, expressing in terms of dB, we get SNR output in terms of dB for the post filtered condition is equal to 10 log 10 of 498.3. This reduces to 26.97 dB. This is the answer for the post filtered condition. Right. With that, we have come to the end of this video. If you like this video, kindly like and share this video and subscribe to my channel for more information on digital communication. Thank you for watching. Have a good day.